Okay, YouTube, in this video we're going to discuss exponential functions in general and kind of explore what their graphs look like, kind of trying to describe their nature a little bit, okay? So let's go ahead and start with what an exponential growth function is, or just an exponential function is. We say that functions of the form y equals b to the x power would be considered to be an exponential function. Now, we consider this to be exponential because our exponent is the independent variable here. So we could see a function that looks like maybe like the one we're going to investigate here first, which is y equals 2 to the x. This would be considered an exponential function because of the fact that that x is up in the exponent there. So when we look at functions of this type, let's consider what it is that we're doing here. As a matter of fact, we're taking 2 times itself, a given set of times that's dictated to us. So what I've done is I've already constructed a t-chart here with some independent variable values that we'll plug in, and we'll talk about how the values of this function behave as x goes up by 1 every time. So let's start with this. We say, how about 0? 0 is an easy one to plug in. If we were to say, what is, f of 0? We would say, well, that's y equals 2 to the 0, which is, of course, is 1. Okay, so if we were to say, well, then y equals 2 to the first here, we would get 2. And y equals 2 to the second, we get y equals 2 squared. This would be 4. And if we, again, were to do y equals 2 to the third, of course, we would get 8. And we can see that every single time x is going up by 1 here, the idea is that we are not adding the same number every time, but we're multiplying by the same number every time. And not are we just multiplying by any number, we're multiplying by the base of this exponent right here, which is this 2, okay? And that's why we typically give it the letter b when we represent it, formulaically. So we say, all right, y equals 2 to the x. I know that every time x goes up by 1, these are multiplying by 2. And we've seen this before. As a matter of fact, if you've studied sequences and series, we'd say this is just a geometric sequence. It's just that I'm allowed to plug in more things for x than just integers. I can plug in 1.5. So now going backwards, if the reasoning is every time I go up by 1 with my x, my y's are getting doubled, then going backwards you can see how it would be just the opposite. We would be dividing by 2. So 1 divided by 2, we would get back here, we would get a half. But does that make reasonable sense? Remember that when you take 2 to the negative 1 power, for our x value here is negative 1, then we get this. We say it's the same as 1 over 2 to the positive 1. We'll just put this downstairs. We'll move it. Okay, so this would be a half. 2 to the negative 2. The thing with exponential functions is the same as 2 to the positive 2. It's just that it's its reciprocal. So we would say, more generally speaking, when you have a negative exponent, it's the reciprocal of that thing, and then you could just take that thing to that power naturally. So like 2 to the, negative 4, well, 2 to the 4 is 16, so 2 to the negative 4 is 1/16. So graphing these points, let's take a look at this. We see 0, 1 is on our graph, so that'd be this point right here, 0, 1, 1, comma 2, and then we said 2, comma 4. So you notice that this height right here doubled as we go to this next point, and then this height of 4 will double as we go to this point here. This has got to be 3, 8. And then going backwards, we had negative 1 1/2, negative 2 1/4, negative 3, is an eighth, and I have a hard time drawing these so small. But if we were to keep going to the left here on this graph, what I want you to notice is with exponential things, it'll never reach a height of 0. This thing could be divided by 2, divided by 2, divided by 2, going backwards instead of multiplying by 2, but it will never reach a height of 0. So what we're going to do is we're going to put this imaginary horizontal line on the x-axis here. And this horizontal line, we're going to refer to this as a horizontal asymptote. And an asymptote, more generally speaking, is a line that a graph typically approaches but never quite gets to. So our graph, if we were to draw its basic shape, we say it is growing, look at this, exponentially, because it is speeding up how it is growing. And we would want to label this y equals 2 to the x power. But we see that this is a general shape of an exponential graph. Shape of exponential growth is this idea that it's just going to keep compounding on how it grows each time. So notice that the end behavior of this graph, we say as x goes to positive infinity, that is, as our x values get bigger and bigger, x approaches positive infinity. What's happening to our y values here? We say f of x, or our y values, are approaching positive infinity. So we say f of x values on the right side are approaching positive infinity as x values are going to the right. And as we go to the left, we say as x approaches negative infinity. We say what's happening to our f of x values? Well, you notice our y values here are approaching a height of 0. So we actually say that f of x approaches 0, which means that the graph does have the line y equals 0 as an asymptote. Okay, so I would say that this happens with any exponential function. We could have y equals 3 to the x, and it would have a lot of the same characteristics of this graph right here, but mainly the same characteristic that I want to highlight here is that it has the horizontal asymptote at the x-axis. Okay, So from left to right here, I do want to consider this question. Was our graph moving toward or away from the x-axis? That was, as we read this graph from left to right, we see that our graph is going upward here. So we say we're moving away from the x-axis. In other words, our y values are growing. Okay, so I want to label this here, and we're going to call this exponential growth. We will see decay in the future, but for now we're going to call this growth. And you can always tell because your y values are increasing in size. That is to say, we could have had a graph that did this, which is that we didn't, but this would still be growth because it's moving away from the x-axis. Alright, so really quickly here, it says graphing calculator activity. We can just throw this online on desmos.com. But I've got the graphs of y equals 1/3 times 2 to the x and y equals 3 times 2 to the x. And what we're going to do is we're just going to relate this back to the graph of y equals 2 to the x and kind of make our sketches here. So here's what I'm going to do. I'm going to open up our graphing calculator here, Desmos. And we're going to put these in. We say y equals 2 to the x power. Here's our basic y equals 2 to the x curve. Let's do this here. So we notice it goes through 0, 1, and 1, 2, and 2, 4, and all that fun stuff there. There's one highlight there. 1, 2, and 2, 4. If we were to do 1/3, y equals, I'll put this in parentheses, 1 divided by 3, and then we say that times 2 to the power of x. Then we get this blue graph right here, okay? And if we were to say y equals 3 times 2 to the x power, what I want everybody to see here is that we're getting the same general shape, except for the one thing that's a little bit different is this: it didn't start at the point 0, 1. Okay, so we notice that this green graph here started at a height of 3, and this graph down here started at a height of, well, you can kind of see it right there, 0.3333. So that 0.333 corresponds to this 1/3, just as this 3 corresponds to this 0.3. Okay. So we say that most normal graphs, or we say the parent function, which is y equals 2 to the x, we didn't do anything to it, we didn't put a number out front, it goes through 0, 1, but the moment we add a coefficient out in front of this, we say that we're going to get that value, like that 1/3 or that 3, for the height of our graph for its initial point. Okay. So the reason why, let's talk about why this happens. Because when we take, say, y equals 2 to the x and we say we plugged in 0 here, we notice that we got 1 for an output. So the moment I say, what if I were to take, say, 3 times 2 to the 0? We would do our 2 to the 0 first, but then we would have to take that times 3, and anything to the 0 is 1. So that 3 is directly going to influence, then, what you would get for an output there. Okay, so we would say, in general, we say y equals 1/3 2 to the x. We said it was at a height of, 0, 1/3, and I had this graph that had the same asymptote and increased here. And I had another graph that was at y equals 3 at that initial point, and then our initial graph, y equals 2 to the x, was here. Okay, so we say that y equals 3 times 2 to the x is this one up here. Y equals 1/3 times 2 to the x down here. So we can see that this value out front here has a direct impact on how our graph looks. So using that knowledge, we say, well, I don't know, I want to graph y equals -1/5 2 to the x and -5 2 to the x. Let's make a sketch of each and compare with the graph of y equals 2 to the x. Well, y equals 2 to the x, remember, goes through 0, 1 and has an asymptote on the x-axis. So we say this is roughly y equals 2 to the x here if I'm just throwing together a sketch. The thing we just discovered was this. Instead of going through 0, 1 on these ones here, they're going to go through 0, whatever this value is out front. So for instance, this graph right here is going to go through 0, -1/5 right there. And this other graph right here is going to go through 0, 1, 2, 3, 4, 5, -5. Okay. So to see how these graphs compare, what I'm going to do is I'm going to also put these in here. And recall that these values out front now are negative, these coefficients. So we say y equals, in parentheses, -1 divided by 5. And we say I'm taking this times 2 to the x power. Let's see if I have to put in a multiply sign there. I do. Okay, so we say y equals -5 times 2 to the x. It makes sense, it asks for 1. You'll notice that these graphs actually open downward, which is not changing their basic shape. These are still growing, but they open downward. And the other thing I want to point out here is this. Look at this. We say this is -1/5 right here, and this is -5. So again, this coefficient, not the base of this value here, but the coefficient out front is really directly dictating where our y-intercept seems to be. So when we sketch these in here, we would say that our other two graphs essentially look like this. We had one that was a little bit flatter but still exponential growth, and then one that still had the same asymptote but kind of came in more sharply, kind of like that, okay? So in this activity, what do we want to kind of observe here? Well, exponential functions, we say they grow exponentially away from the x-axis. They have a horizontal asymptote on the x-axis, okay? So we say the x-axis is a horizontal asymptote, and we say also that the graph always passes through the point 0, a. Now, when I say a, I'm saying, of a graph, and it's kind of hard to read there, it looks like this. We looked at 2 to the x. I'm going to say more generally speaking in the next video y equals ab to the x, where this a value here was telling us where our y-intercept is. So we're always going to kind of look for that, okay? And then we say that the domain of these graphs, they go from left to right forever and ever, so the domain is all real numbers. And we say if you were to look at just the graph maybe of just y equals 2 to the x, its range would be everything from 0 on up, but not including 0 because it never really reaches a height of 0. So in the next video we'll talk about the shape of this graph more generally speaking and throw together some quicker graphs. Cheers.